Okay, this is cables. So for cables, we need to make a few assumptions. And that is that they're perfectly flexible, and inextensible. Alright, so the tensile force acting in the cables is always tangent to the cable at points along its length. So the tensile force acting in the cable is always tangent to the cable at points along its length. And once the load is applied, the geometry of the cable remains unchanged. And the cable, or segment of it, can be treated as a rigid body. So let's say we've got a hook at A that there's a cable attached to. It goes down to point C. From C it goes down to point D. From D to point B. Also attached to a hook right there. Let's say from the height from A to B is H. From Y there's YC and YD. And there's P1, a load acting right there, and a load acting right there, P2. We know this length, and this length. So let's say you had been given your height H, all of your lengths L1, L2, and L3, and your external loading P1 and P2. And now you would need to find your reactions at the loops, which would be AY, AX, and BY, BX. And then the tensile force in the cable, which would be TDB, TCD, and TAC. And then also we need to find YC and YD. So if we were to look at each of the points A, C, D, and B and sum the forces for each of those points, so if we sum the force at A, B, C, and D, we would have a total of 8 equations. Sum the forces in the X and Y direction at each of these points. But we have 9 unknowns. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we would need to use the Pythagorean theorem to find the last variable. YC or YD. So this problem, as it's stated, is actually very complicated. And it actually, you need to utilize a computer to solve it. However, a lot of times if they were to have given you YC or YD, then it becomes less complicated and you can just use your sum of your forces to find your other unknowns. So I personally will not give you any problems that you need a computer to solve. So the other thing that we can do for a cable is subject it to a distributed load. So let's look at that. A cable subjected to a distributed load. Let's say this is our x-axis and this is our y-axis. Got our hook at point A, and the cable goes out to a wall at point B. And it has some distributed load all along its length. So we're going to call this W equal W of X. And then we're looking at some point X along the cable, and this is delta X. So what I would need to do is draw a free body diagram of that delta X segment. So this is my cable. We would have the tensile force. This would coincide with the x-axis, and this difference right here would be theta. Then on the other side, we would have the tension plus the change in tension. And with its horizontal, that would happen at theta plus delta theta. This height difference would be delta y. This segment is delta x, which is just a snippet of the last diagram. Then this entire length is called delta s. So the length of the cable is delta s. And then we would have our distributed load of W of X times delta X, and that would happen at K delta X from the end. Alright, so if we sum the forces in the X direction, we would get negative T cosine of theta plus T plus delta T times the cosine of theta plus delta theta. That'll be equal to 0. The sum of the forces in the y direction would be equal to, let's see, negative T sine theta plus T plus delta T sine theta plus delta theta. And then also we would have minus W of X delta X. And then finally we'd have the sum of the moments about point O, which would be 0. And this right here would be our point O. So if we were to sum the moments about that, we would have W of X times delta X times its moment arm of K delta X going counterclockwise. We would have the horizontal component of the T, so T cosine theta. Its moment arm would be delta Y. and then we would have plus t sine theta times its moment arm of delta x equal to 0. And so next we would divide by delta x, and we would also put all of our deltas equal to 0. Delta x goes to 0, delta y goes to 0, delta theta goes to 0, and delta t goes to 0. So after this, if we were to look at this equation, our delta theta would have gone to 0, or I'm sorry, so negative t cosine theta plus t cosine theta would have canceled out, such that all that we were left with was d t cosine theta over dx is equal to 0. In our y component, the same type of thing, the t signs would cancel, such that we would be left with d t sine theta dx minus w of x is equal to 0. Then finally, if you were to divide by delta x over here, you could get dy over dx is equal to the tangent of theta. So if you integrate this, you would just get that t cosine of theta is equal to a constant. And we're going to call that constant fh. Then do the same thing over here, integrate this, you'd get t sine theta is equal to the integral of w of x dx. And now, if I wanted to do t, so if I divided the whole equation by t cosine theta, I would get the t's would cancel, and over here would be tangent of theta, which is also equal to dy over dx, and I divided by t cosine theta, which is the same thing as f of h, or fh, sorry. So I integrate this one more time, and I would get that y is equal to 1 over fh times the integral of wx dx dx. And then, so you're integrating twice, so we would, the integration constants can be found using the boundary conditions. So this equation will be used when your cable is subjected to a distributed load. So now, what if a cable was subjected to its own weight? So we'd have a free body diagram of the same delta x. Its weight would just be like a distributed load. However, rather than it acting over delta x, it would act over the length, so w of s, delta s, because it would matter the length of the cable, not necessarily the x component, because the length tells what the weight is going to be. So that happens at k delta x from the end. We're going to have t plus delta t, theta plus delta theta, Down here we'd have T theta. This would be our delta S. This would be our delta X. Right here would be our delta Y. And now what we'd want to do is put delta S going to 0. So if you were to do the whole thing that we did last time, you would end up with T cosine theta is still equal to f of h, FH. T sine theta would be equal to the integral of ws ds. And then dy dx would be equal to 1 over f of h times the integral of ws ds, where ds is equal to the square root of dx squared plus dy squared from the Pythagorean theorem. If you were to divide by dx squared, you could get ds over dx squared equals 1 plus dy over dx squared, and then get that dy over dx is equal to the square root of ds over dx squared minus 1. So now we have what dy dx is. We plug that in over here, and we get that the square root ds over dx squared minus 1 is equal to 1 over fh is the integral of w of s ds. Square both sides of the equation, we get ds over dx squared is equal to 1 over fh times the integral of w of s ds squared plus 1, and then we'd have to square root the whole thing, so ds dx is equal to 1 over f of h times the integral of w s ds squared plus 1. Oops, this should have just been that. To the 1/2. And then finally we could put that on both sides of the equation, and we get that x is equal to ds over 1 over f of h times the integral of ws ds squared plus 1 to the 1/2, and all of this as the integral. So you can use this to solve problems where the cable is subjected to its own weight.